Okay, in this video I'm going to introduce you to an application, a very common application of two-dimensional vectors, and that is objects we call projectiles. So what is a projectile? When I'm talking about a projectile, I'm talking about any object that's launched, thrown, shot into the air, no self-propulsion. So the only force that gets it moving is the initial thrust force that gets it in the air to begin with. But once it's in the air, it's only under the effect of gravity. So truth be told, it still is under the effect of air resistance when it's traveling through the air. So the faster something moves through the air, the more drag air resistance will have an effect on it. But for the purposes of our introductory problems to projectiles, we can neglect the effect of air resistance that is very minimal, so that we get a nice clean set of algebraic equations to solve. We don't have to apply calculus quite yet. So a projectile, like a ball kicked in the air, right? Applications in sports, pretty much every sport: basketball, volleyball, baseball, soccer, golf, right? Anything that hits a ball or throws a ball into the air has an application of projectiles. Shooting a bullet, right? Throwing a rock off a cliff, right? These are examples, or even jumping off a cliff yourself, right? Your body becomes a projectile. Or if you're jumping off of a ski jump, or if you're jumping off of a bike jump, right? BMX, if you watch X Games, those skateboarders that are doing the super high jumps, they become projectiles, right? Their bodies become projectiles once they launch into the air because they're only under the effect of gravity. So let's look at some examples for how we can have a projectile. Let's take a soccer ball, and in this case we have a cliff. So kids are playing soccer near a cliff. Not a good idea, right? Should warn against that. But it makes for a good problem, so we're going to use it. Kids are playing soccer near a cliff. They kick a ball, and it has an initial velocity that's horizontal in this case, meaning it's all x direction. And it's launched off the cliff, and then it travels to the ground. We want us to look at what is its path going to look like if it's only under the effect of gravity through the air. Well, gravity, if we learn from the last unit, always pulls things down, straight down, towards the center of the earth. So if my ball is only under the effect of gravity, if I were to remove gravity, right, it will keep moving in this straight line path, but as soon as I take away the cliff, it's going to start falling due to gravity. So a couple interesting things. One is that, and I'm going to use a little ruler to help kind of chart this out. Let's say every 2 centimeters. As it falls through the air, it's going to begin to accelerate. So I'm going to have a shorter distance traveled in the first, and then a larger, and then a larger, and then a larger. Now I'm not doing that exactly to scale. I didn't solve that out, but relatively to scale. The ball is going to fall a greater distance every second in the y direction. But in terms of its horizontal motion, remains constant. There's nothing accelerating it in the horizontal direction. So if I were to look at its horizontal velocity, so let me just draw the horizontal velocity vector. At any stage of its flight, it doesn't change. So the distance from here to here to here, let's just say it's 4 meters per second. And every one of these is a second. It's going to go 4 meters to the side, 4 meters to the side, 4 meters to the side. That velocity to the side direction will remain constant throughout its path. But it's under the influence of gravity in the downward direction. So here, my initial y velocity is 0 because it's only launched horizontally. And then as it falls, it begins to gain a little y velocity each time. A little more, right? So by the time it gets to the bottom, it's going to reach its greatest y velocity. So the magnitude direction version, it's the absolute velocity of the projectile. If I draw what that velocity vector would look like. Right, it continues to increase. This is the velocity of the ball as it goes through the air. So accelerating downward, but moving at a constant speed left to right. Now you'll notice, this is not a really good picture, but it begins to form a curved parabolic path. Now why is that? Why does it form a curved parabolic path? So here's a little bit of an aside. Okay, if you think about what we know from motion, if I'm moving at a constant speed, my change in position is only proportional to time, right? If I looked at change in position is time times velocity, whatever, if I'm moving at a constant speed. But if I'm moving at a constant acceleration, such as negative 9.8 meters per second squared, as in my y position, it's proportional to the time squared. So if I did the algebra and I wrote y as a function of x, so I combine these into a single equation, what I would get is the parabolic form of the quadratic, well, the quadratic equation, which takes a parabolic shape when you plot it. So that's why my projectile takes a parabolic path through the air. Okay, so that's a look at what if I kick something at a horizontal velocity and it maintained that velocity while it increased in the y direction. What if I shoot something or kick the soccer ball off the ground with some initial velocity? And I wanted to see what happens to it then. Well, it turns out it's still going to maintain that same velocity that it initially has in the side-to-side direction. It's still going to accelerate in the downward direction, in the y direction. So if I plotted out this path, it might be here. It's going to cover a little less distance, and then it's going to start falling back down. Something like that, right? So what's happening here? Well, what's happening is it has an initial y velocity and some x velocity. I should have been consistent here and kept the black. And the x stays the same throughout its flight. So it covers the same 4 meters side to side every second, so long as my x velocity is the same as it was here. But now the y velocity, as it goes up, gravity is always pulling down. So something moving upward has a negative acceleration due to gravity, so its velocity is going to get a little bit shorter, Vy, over time. Up here, it's going to get even smaller. Now here might be its peak, so that's a point where Vy is 0, just like a free fall problem. And now it's beginning to fall back down, so it's got a small Vy, and then a little bigger Vy, and then still larger Vy as it goes towards the ground. So what are some of these key rules for understanding projectiles that will allow us to solve problems? Well, we know that a projectile has an x acceleration of 0, so we got to look at the x, what's happening in the x direction, what's happening in the y direction separate. We know there's nothing accelerating in the x direction. It maintains a constant x velocity throughout its flight. But we know that in the y direction, it's under the influence of gravity, which is a negative 9.8 meters per second squared, always down, which causes it to gain a greater distance towards the ground, a greater y velocity towards the ground every second that it's in the air. Same thing here. If I kick it with some initial y velocity up, it's going to lose that velocity on its way up, and then it's going to speed back up on its way back down. So I do have a change in y over time, but in x, I don't have a change in, or a change in Vy. I'm sorry, a change in Vx is 0, right? My initial x velocity is my final x velocity is the same x velocity at every point in its flight. Right? This is always V naught x. But there is one thing that will be the same when we do these problems, and that is the time. Right? The time that the object is in the air, or the time it takes to get from this point to this point, will be the same no matter whether I'm looking at the x direction or looking at the y direction. So that is one rule that we're going to use to connect the two seemingly independent motions of the x and the y. So that's a little bit of a background. In the next set of videos, we're going to look at how do we solve some of these problems using the rules that we know about projectiles.